Thanks, Eric. So I'm going to start off today by finishing the calculation from last time. So last time we were looking, so let me write that down, calculation. So last time we were trying to find a good estimate for a given average size of the Selmer groups in a family X. So we have D ranging in X, looking at the isogeny Selmer groups of ED. Okay, and so buried in this is a lot of notation. So first off, phi was degree 2 isogeny of elliptic curves over Q. And in general, the isogeny Selmer groups in a family don't behave particularly nicely, so we added an extra assumption to make his isogeny Selmer groups behave nicely, which is we assumed that the two torsion rational points of both the curve and the isogenous curve were isomorphic and equal to z mod 2z squared. Okay, so that was one thing we assumed. And just a bit of notation that might have been nice last time as well, is I'm going to use this set V to denote what I was calling the bad places from last time. So these are 2 and infinity, together with the places of bad reduction for E. And so next up is the set X. So what are we looking at? Well, X is a product space of the form x1 through xk, what I sometimes call a grid in my work. And in this grid, x1, or each xi, are disjoint sets of primes. Not meeting D. And we made many assumptions, including one that Ariel pointed out last time and that I forgot to put down yet again. These are finite sets because we want a nice finite sum at the end. And the way we think about a D inside of this product space is we both think about it as a tuple, so P1 through Pk, and also as a product. So we use these sort of interchangeably. Here we're thinking of it as a product, but when we talk about an element, D and X, we're thinking about it as a tuple. Okay, and then on top of this, we made some assumptions. So for convenience, take A to be the product over all the finite primes inside of D. And so the assumptions we were making was first, we wanted the primes in each of these intervals to sort of behave the same at every prime in V. And the way that you enforce this is you say that A, the Legendre symbol of A over Pi equals the Legendre symbol of A over P prime I. And this needs to hold for Pi, any 2 primes inside of the same interval, and for any I less than or equal to K, and for any A dividing big A. And so, yeah, all the primes inside of a given interval, inside of a given xi, behave the same at the primes in V. The second thing we assumed was we assumed a large sieve style inequality. And I was sort of vague last time about what sort of quality we would want on this inequality. Just sort of to give you some sense of the quality we need, it would be enough to say that this is at most the size of xi times the size of xj times some tiny saving xi to the negative epsilon plus xj to the negative epsilon. Or maybe epsilon is 1000 or something like that. Okay. And we need this to hold for any I not equal to j, and for any sequence of coefficients cpj bounded by 1. Okay. And then finally, there was this assumption that I was making that for all A dividing A, that besides 1, there is an I less than or equal to k, such that A repeat I is equal to -1. And this was a sort of technical assumption, but I'm writing it on the board again because I want to actually more explicitly do a calculation out that I mentioned last time, which was using the Greenberg-Wiles formula to explicitly bound the set V naught to actually enumerate. And so the context of that is we had a parameterization space of V, and this was equal to the square-free classes dividing big A, together with the power set of 1 through k. And the reason why we're defining this is to be able to parameterize things that look like Selmer elements. So throughout this talk, I'm going to use D as sort of shorthand for the tuple P1 through Pk. So I'll write it down here, but in general, I'll think of D as being P1 through Pk. And how we define a map BD for each P1 through Pk, going from V, and it's going to be to the set of B inside of Q cross over Q cross squared, such that the B has odd valuation only at places of V or primes dividing B. And here I'm taking advantage of the fact that I'm thinking of D both as a product or as a tuple. So an equivalent statement to P dividing D would be P is one of P1 through Pk. So we have this parameterization, and every Selmer element that we could encounter lands in this set using the isomorphism between Q cross over Q cross squared and H1 EP2. So yeah, let me write that down. BD the image of BD contains selfie ED under the isomorphism between Q cross over Q cross squared and H1 GQ EDZ. Okay. So this is some setup. And then, so what you can think of the goal as being for estimating the sum is we want to figure out how much of V maps into the Selmer group on average as we vary over D. So we can actually rewrite this if we would like as the sum of D over X and the sum of B and V. And then what we're summing is the characteristic function for checking whether B, D of V obeys all the local conditions. So we have this equality. We're just checking whether a BDV obeys local conditions at the remaining places of Q. Okay. And then as a starting point, we took V naught to be the set of V inside of V, such that BDV satisfies the local conditions. For all places inside of script V. And if we think about what V naught is parametrizing, it is actually parametrizing a certain Selmer group. And so it's a Selmer group of mu2, and then with the following local conditions. So first, we have LV of E d phi. This is the local conditions being parametrized, and this holds for all the bad places. And then for primes dividing D, we see that the local condition is everything. So H1 GV E phi. And so this holds for P dividing D. And then at all remaining places, it's the unramified local conditions. So V naught has the same size as this Selmer group. The idea here is that if instead of LV E d phi up here, we just had H1 GV E phi, an alternative description of this would be the set of B in Q cross over Q cross squared, which only ramify at either the places in V or the places dividing D. And this is precisely what V was parametrizing over here. And so all that we've done, going from V to V naught, is we've imposed local conditions at the primes of V. And so that's where these are coming from. Okay. And so, yesterday, I told you you could find out some ratios of these things. We can find the ratio of the size of this to the size of the dual Selmer group. Okay, and so how do we define the dual Selmer group? Well, in this case, we're just taking the Pontryagin dual's twist of mu2, which is mu2 again. It could also be z mod 2z, but that's the same thing. This local condition, I mentioned last time that the dual local condition to an isogeny Selmer local condition is the local condition of the twist. So E naught D V naught for the dual isogeny. So that's for V and D. And then the middle condition is 0. The orthogonal complement of everything is nothing. So that holds for P dividing D. And finally, the unramified local conditions are orthogonal to the unramified local conditions. Yeah, E d phi. Okay, so this is the ratio of two Selmer group to the size of the dual Selmer group. And what we discovered, or what I mentioned last time, was that this has an explicit formula. This can be written down in terms of the ratios of the sizes of these local conditions. If you work through what that says, this tells you that the ratio is equal to 2 to the k times the product over all the particularly bad places, V and V, of the size of LV of E d phi. 1/2 over the size of the local conditions for E naught D phi naught. So this is at least something explicit that we've written down. And now the thing to note is anything in this group is going to be trivial at the primes dividing D. It's going to be something, a B in Q cross over Q cross squared, which is locally a square at all the primes dividing D. And unramified at all primes except for the ones in D. And so, because I've made this technical assumption, this denominator is actually 0. And so we're just left with the formula that V naught is... What?
It's 1, not 0.
Oh yeah, right. What we're left with is that this formula explicitly gives you the size of V naught. And this sort of thing, where you have a Tamagawa ratio showing up in the size of one of these things, is very normal. When you look at the quadratic twist family of any sort of Galois module and look at how the two summer groups are distributed, you sort of expect Tamagawa ratios to appear for exactly this reason. They sort of show up in the size of the parameter spaces. Okay, great. And so that's nice. The next thing we want to do is we can now restrict our sum to just be over V and V naught, because these are the only ones that obey the local conditions at the bad places. And we are looking at what we now need to check is we need to check for each of the primes pi that the cocycle parameterized by V obeys the local condition at pi. So I'm just going to write that down. So this sum of products of these characteristics functions equals the sum of the sizes of the summer groups. And so last time I said that BDV obeys the local condition if and only if either BDV lies in QPI squared or some constant A2 fixed by our elliptic curve times D times BDV lies in QPI squared. So this is the local condition, at least at the level of elements inside of Q cross over Q cross squared, that we're imposing at these remaining places indexed by I. If you recall, the way the parameterization works is that we have an element A inside dividing A and a subset T. And this corresponds to the element A times the product over T of Pi. That's how we get an integer. And so the integer, we're going to want to check this number under the circumstance that I is not in T. And if I is in T, we're instead going to check this number. Because if I is in T, then this number is has odd valuation at Pi. So it definitely can't be in QPI squared. So only the other one can. So exactly one of these numbers has even valuation at Pi. So we should be looking at that number. With that in mind, I'm going to use xi as notation just for A times I and T of pi. I guess I'm using the same index a couple times. So for j less than or equal to k, I'll take xj to be just the thing parameterized by BDV.
On xi you're correct.
This is trying to be a little xi, but I will call it something else. Kappa j. So kappa j is going to be just BDV if j is not in T. And if j is in T, then we're going to use A2 times D times BDV, which you can work out. You have an A2 times A out front, and then you have a product over all the primes not in T. So this is what we're going to use if j is in T. Okay. With this notation set, this sum can be rewritten in the form V in V naught, then the sum of D in X, and then the inner product. So far everything has stayed exactly the same. But now I'm going to rewrite this local condition in terms of the Legendre symbols, and I'm going to write it as 1/2 times 1 plus the Legendre symbol of xi over pi. The idea being that this is equal to 1 if xi is a square, which is what the local condition requires, and this is equal to 0 if the local condition is failed.
xi is kappa I.
It sure is, because I will never remember notation I changed in talk. Yeah. Kappa I. Thank you, Newton. And so the next step, we have this lovely sum, is we're going to FOIL it. So we have this big product, and we're going to expand it out as best we can. So when we expand out this inner sum, we have a choice for each I less than or equal to k of whether we're going to pick the 1 term or we're going to pick the Legendre symbol. So that, yeah, that's sort of a coin flip for each I less than or equal to k. And so when you expand this out, you end up with a sum over subsets of 1 through k. So to write that out, we have sum v and v naught, and then a sum over subsets of 1 through k. And then I've been sneakily bringing the d sum in over the course of the talk. Remember, at the beginning it was on the outside. Now it's right where we need it. And then on the inside, we have a product over the I and R of the Legendre symbol of kappa I over pi. And then we have this 2 negative k term from collecting the 1/2 for each of the primes d1 through pk. Yeah. So this is now what we are estimating. And we finally have something where we actually can apply assumption 2. So assumption 2 was saying that we have good bilinear estimates for the Legendre symbol. So if we're only considering one of these terms, so for a fixed v and a fixed r, just considering this innermost sum, that's going to be small so long as it has some pi over pj appearing non-trivially. And what that means specifically is that pi over pj appears, but pj over pi doesn't, or pj, vice versa. We need to care about that because of reciprocity. So what we find is given v equals at and r, this inner sum has pi over pj XOR pj over pi term for some I not equal to j, if and only if, well, first, the set T is not the empty set and also isn't everything. And ditto for the set R. So if these two conditions are satisfied, then this inner sum has a non-trivial pi over pj term. And because of that, we can remove them from consideration using assumption 2. So by assumption 2, the only contributing terms are first the ones where T is either empty set or where T is equal to everything. So T is equal to empty set or everything. And so this happens for exactly two choices of V inside of V naught, because somehow the local conditions at V prevent other weird A. Sorry, I won't get into that too much. T equals empty set or 1 through K. The main term being contributed from these is 2 times 2 to the negative K from this term here. But with these terms, R can be anything, so that's the size of the power set of 1 through K. And then times X. And so these two parts cancel out, and we're left with 2X from this term. So the empty set and 1 through K examples of T contribute a 2X. And then the other case where we can't use the second assumption to say something is when R is equal to empty set or 1 through K. So in this case, our choice of V and V naught can be anything. And so we have V naught total choices of what V is, I guess -2 to avoid the two cases that we've already considered. Okay, so our sum over V becomes the V naught -2 term. We have the same 2 to the negative K as before. Yeah, our innermost are the only sums, the only R that we're looking at are empty set and 1 through K. So that's another multiplication by 2. So we have our two main terms. We have a 2x and we have this weird expression. And everything else is negligible because of assumption 2.
Do you think where you get that 2 from? So if R is empty, it's just the empty product. If R is everything?
So this 2 you mean?
Yeah.
So there are V naught -2 choices of V that because we're summing over V naught and we've already handled 2 of them, empty set and 1 through K. And then there's 2 choices of R that we're considering in this term, both the empty set and 1 through K. So V naught -2 times 2, and then the only other term that matters is this 2 to the negative K.
And then the product is, okay. So
In this case, this is not trivial to see, but it is true that like it is when T is the empty set or when T is the empty set or when R is the empty set, it's clear that this product is 1. Much less clear is that when T is equal to 1 through K or R is equal to 1 through K, that this product is also 1, but that is true.
That was so.
Yeah, no, there's a reciprocity thing happening behind the scenes, which is good because we couldn't actually handle those terms otherwise, because in that case, I think we end up with both a PI over PJ and a PJ over a PI. So going through these calculations, especially in the most complicated setting, there are a lot of miracles that happen that sort of like, oh, we couldn't control this, oh, but that's okay because like it's secretly equal to 1. The most extreme example of this comes from something called involution spin, which if involution spin was not Chevatarov, I would not have a result, but it is. So so I just tried to prove that for like 6 months and eventually got it. It's like totally random, but whatever. Sometimes things work out. But to say, finally, I started this lecture. Was midway through last lecture when I asked, we're summing the size of the Selmer group, the Selmer group, over this twist family X. How big is it? This is approximately 2 times X plus, and we have this wonderful formula for the size of V naught, including the 2 to the k term, which cancels out. So we end up with a 2 times product of V, that's LV, whatever. 2 times squiggle T times X minus some negligible term, like about on the order of 2 to the negative k. So this is our final answer to this question. Okay, great. So that's sort of the gist for how you find a Selmer moment. But we want to find the Selmer distribution. And if we want to find the distribution, we're going to need more than just the average size. So let's do the same thing. But instead of looking at the average size, we are going to look at the average mth power for some m greater than or equal to 2. So this is the new thing that we're going to try to evaluate. Okay. So the starting point is we want to be able to parameterize m tuples of possible Selmer elements. So last time we parameterized single elements, and this time we want to parameterize m tuples. So the map that we can set up is just going to be m copies of the map we had before. So BD will go from tuples of a divisor of big A and something in the power set of 1 through k. M. And what we have is that this gives an isomorphism to the set of phi1 through phi m inside of H1 GQ of ED phi to the m, such that each phi is ramified only at places in V and primes dividing V. So we have another parameterization for m tuples of Selmer elements. And so the thing that we're actually going to be evaluating for this mth moment is we're going to be summing over this new vector space V And what we're going to be summing up is we're going to be checking whether this M tuple V parametrizes an M tuple of phi Selmer elements of ED. So we're going to be summing this up over the grid. And same as before, the way we're going to do this is we're first going to consider the places in V. We'll do some Tamagawa number thing using the Greenberg-Wiles formula to get an estimate of the corresponding size of V naught. Then we'll just have to check the places at the primes in B, D. That'll give us something of the form V and V. And then now R is going to be an n tuple of subsets of 1 through k. Yeah. So yeah, R is an m tuple of subsets of 1 through k. And then there's going to be some pairing between V and R that depends on the twist D. We're going to get another expression like this. And we're going to be summing that up over all D. Okay. August, you have a question?
Where's V naught?
Oh, I guess, yeah, to do this correctly, I better make this a V naught.
Oh, okay, that's
Yeah, I haven't defined V naught, but yeah, if I did, this would be right. And then, okay, now we're going to separate the VR which contribute meaningfully to this sum from the VR that we can control using something like the large sieve. Yada, 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 you get a moment, et cetera, and then from this, you can basically find all of the nth moments in this family. What I'm sort of trying to emphasize now is that this is difficult in the sense that it's kind of hard to keep track of everything sort of flying around, but it's not difficult in the sense of like introducing entirely new ideas to handle these higher moments. We're still using a parameterization, we're still going through a character sum, and at the end of the day, we're going to get an expression for these moments that involves certain Tamagawa ratios and behaves nicely sort of as before. The one thing that I'm sort of going to gloss over is something called the moment problem, which is what this will tell you in the end is it'll tell you the distribution of moments of Selmer groups in this family X. But can we reconstruct the distribution of ranks from this? From these moments. And there are in general a lot of subtleties for this question, but for this particular instance of the question, the answer is yes. The moment problem has only one solution for the sort of moments you get from these calculations. In other cases that I've handled, the moment problem has a bit of a more subtle resolution, but all I want to say about the moment problem for right now is that it exists, but in general it is usually easier to calculate moments and then figure out the moment problem later. So more generally, what we were doing in this example was I was using a parameter space for n tuples of Selmer elements. And this is, you can sort of write down explicitly what this looks like in this case without too much hassle, because this Gala module is just one copy of F2. A nice thing about this setup that I've given you so far is that it does apply to more complicated torsion structures than just trivial Galois modules. But the technology for doing so, I developed in my work, and it is the part which everybody finds to be really hard. So I just sort of want to give a explanation of, at a high level, what's going on in these parts of the argument. So this will be so what I want you to think about sort of as the key example, since it sort of has all the structure that we'll need later on, is we're going to suppose that we're looking at an elliptic curve E with no rational two torsion. Over Q. So a generic looking elliptic curve over Q. And now I want to give you some schematic for understanding just, again, the first moments inside this twist family, where X is the same grid as before, V is still the bad primes of E. And so the starting point here is to set up some sort of parameterization. Let me just say that X is equal to X1 up through Xk, sort of as before. So here's a proposition. For each G inside of this grid X, we can define a natural parameterization map. So same letter as before, and then we're going to have a fixed vector space V. V isn't going to change as D varies, but the map BD will. And BD will give us an isomorphism between V and the set of phi inside of H1, the cohomology of the two torsion of E. And just as a reminder, this D does not actually affect the two torsion. I'm sort of like keeping it around, but it's a Galois module, it's not changing. And it's going to be a parameterization for the set of phi inside this Galois cohomology group, such that phi is unramified at all V outside script V, so the set of bad places of and the primes dividing D. So we have this fixed parameterization over the grid. Then the second proposition is given some point inside of V, and I less than or equal to K, we can check whether we can check whether BDW satisfies the local conditions at Pi from the value of certain generalized Legendre symbols. And my notation for these is going to be the same as in my large Selmer group papers. I'm going to use square brackets. And of course, this proposition is quite vague. What you should be thinking about is, in the calculation I had before, the way we checked whether BDW obeyed the local conditions at Pi was we first multiplied it by A2D if necessary to get rid of ramification at Pi. And then, yeah, we checked whether that resulting kappa I was a square by using Legendre symbols, just regular old Legendre symbols. And each of those terms, kappa I over Pi, themselves decompose into Legendre symbols Pi over Pj. Or Pi and J both vary. And so what I'm trying to say here is that the same thing holds even in this more general context. We can still figure out with our parameterization whether something holds from the Legendre symbols. The definition of the Legendre symbols, the same as the definition of the parameterization, is really hard. So I will not be saying more about it. But I will give one final proposition. Which is given I and j both less than I not equal to j up through k, and given any function f from the set of possible generalized Legendre symbols pi to pj to the interval -1, 1. So given any function on the set of all possible symbols with average 0, so the notion of average makes sense. Even in these more complicated situations, the Legendre symbols are still going to be valued in a finite set. So average 0 is totally fine to write down. And given any function with average 0, we have that the sum of pi over xi of the sum pj in xj of same as before, we have coefficient cpj, and then we have our function on the Legendre symbol pi pj. And this function should be unbiased in the sense that it has average 0, and the claim is that this shows some power saving, has a power saving estimate. And to be precise about that, let me write this in the form max of xi times max xj times max xi to the minus epsilon plus max xj to the minus epsilon. Okay, and so you'll remember that these sorts of large sieve estimates are what allowed us to make so much progress on the previous type of Selmer estimates. And so what I've put in these three propositions is actually enough to carry out the recipe to figure out what the moments of a Selmer group are, of a two-Selmer group are in a quadratic twist family, At least in the case where your quadratic twist family has this lovely form of x equals x1 times up through xk, and where x1 through xk are all pretty big intervals, so that this estimate applies. And this is really all you need. It's complicated, but it allows you to attack general two-summer groups pretty easily once you have it all set up.
Sorry, just to understand. So this here is a proposition, but in the previous iteration, this was kind of a property that you assumed on your grids.
Yeah, absolutely. This is a proposition that I guess gives us the relevant property. Previously, we made the assumption on the grids, but by work of Jatila, that assumption was satisfied so long as the xi were all pretty large and not too different in terms of maximum values. So I phrased it as an assumption, but in my head I was sort of thinking it as an application of the large set.
Are all the xi similarly sized?
In this example, to make this happen, yes. But that leads me right into the last thing I want to talk about today. Indeed. Which is the analytic side of things. So what's known as gridding, or what I call gridding. And so the basic idea is, in any sort of question, the thing we're actually interested in, even if we're only interested in the moments, is we would like to look at all of the non-negative integers up through h, and we'd like to be able to control the two Selmer groups in the corresponding twist family. So this is what we actually want to control. Everything I've talked about so far has been on product spaces. And I think one of the key aspects of my work that sort of meant it was able to go further than like previous work was instead of sort of working in the natural twist family, my work immediately goes to product spaces and stays there the rest of the time. And so we need a proposition in analytic number theory to make that possible. And so, we want to be able to study these things. And so here is a statement. Okay, proposition. So this is going to, so let's suppose that E has been fixed. So we're interested in one particular E, and we're going to choose some very large H. And suppose that when we look over a grid, of twist, so D is inside X of a two-Selmer group of E twisted by T. Look at its nth powers. Let's suppose that this average size of the nth power of the Selmer group in a given twist family of a grid is given to within error by some positive constant A. And we suppose that this holds for all X product spaces x1 through xk satisfying some conditions. And so the first condition is on the number of primes. By error check, we know that if you choose a random integer less than n, usually it's going to have about log n prime factors. And so that gives us a good value for what k should be if we want to actually understand all twists up to a given height. So k is approximately a log h. Okay, so that's property one. the second property concerns the sets xi that make up the grid. So either, so this is going to hold for I greater than or equal to k. So for I greater than or I less than or equal to k. Either xi is equal to a singleton pi with pi. This is the first instance of I chose things that worked. Other choices are possible. The choice I made that worked is x, the 1/3 of log h. Works really well for this. So either xi is a singleton prime in this small range. So think of this as growing much slower than any polynomial in h. Or xi is all primes in an interval b to b times some small power, or some small term that again grows, that shrinks with h, but not too fast, because again, this is another term that I chose because it worked. Lots of terms would work, but none of them really look nice. So we have this little interval from b to b times this small constant bigger than 1, satisfying congruence conditions mod A. So remember, we defined A to be our product of bad primes, and so we're looking at all the primes inside of this weird interval that fit into a given congruence condition. Congruence
This
class.
A is not that A, right?
I sure hope not. Oh no! I've ran out of letters again. Okay, I haven't actually ran out of letters. Let's call this capital M. No, that's also bad. Did someone name something?
Zeta.
Okay. Yeah, so we have, we're looking at things equal to zeta. Okay. So this is the second condition. And I guess this condition also we would want bounds on B. So B should be between x 1/3 log h and h itself. Okay. And then we also have conditions 3 through 8. They are very important, but whatever. And so this describes a nice grid, a grid that's like useful for our purposes, where our methods for our character sum methods apply, but ones that also look natural enough. They look in various ways like they actually would come from real integers found in the wild. And so because of this, if we are able to find the moments of the Selmer groups on each of these grids and find that the actual moments are given by this zeta, the conclusion is that when we do the same thing naturally, so sum over all of the twists up through h of the size of the nth power of the Selmer group, we should also get zeta. And the idea here is that you can actually take the integers up through h and carve them into grids and only have negligible leftovers. And so this is something that happens in a particularly analytic section of one of my papers, this specific process. So one problem you should notice about these grids is these don't satisfy assumption 2. And the reason they don't satisfy this assumption is because in order for these to actually look like real integers, I need to allow for small primes. These singleton primes are sort of a mandatory part of the package. And these singleton primes can't fit into a bilinear estimate like this. That just won't work. And so we need something to replace assumption 2. And so what we do is, if xi is a singleton, and we need to control pi, pj, where xj isn't a singleton, we can't use this large sieve type thing. So in this case, we use the unconditional Shepard density theorem. This hiccup actually makes finding the average sizes of Selmer groups in grids, at least in the grids coming from natural families, even more annoying than it would be otherwise. But the point is that this sort of save using the Shepard density theorem turns out to give you exactly enough to be able to finish the problem. And so, yeah, we don't quite get assumption 2. Things aren't quite that nice, but even the grids that appear in nature, we can apply these techniques to. So thank you.
Any questions for Alex?
Does it really matter what you're averaging here for this to...
No. It could be this. Yeah, I guess this particular statement could be your favorite function, and it would be okay. The only thing that matters is, I guess you need a function that can't grow faster than some exponential function in the number of prime divisors. Like if your function was equal to 1 on good grids and equal to infinity off good grids, then this wouldn't work. But any sort of even half reasonable function will obey this proposition.
Do you have a statement that's a generality?
Yes. The way I phrase it is I basically I do this cutting up into grids in such a way that every twist can be on at most 1 grid, so every d is on at most 1 grid, and then I say that the remaining points, that everything that's not on a grid is negligible compared to h. So that's how I phrase the result in my papers.
So I'm just trying to understand how you use this gridding to answer the original question. So in the original question, okay, you split up the specific grid, and you get an answer for this, let's say m equals 1, you get an answer for this average, it's like 2 plus t times the size of x.
Yes.
Which depends on the size of x. But you need it to be like the same, you need it to be the zeta.
And so
it also depends on t.
So that the x appeared in that because in those estimates I wasn't averaging.
You want divided by x, so the x is fine, but you
x
still
is
have this 2 plus 2t.
Yes, and so
change.
the Tamagawa ratio, this is one of the horrible things that goes wrong in, so we did that isogeny calculation in a case where it was particularly nice, right? We did it in the case where the elliptic curve had full 2 torsion and the isogenous curve had full 2 torsion. Wonderful. Because of those Tamagawa ratios, the actual distribution of 2 Selmer groups in the full quadratic twist family is something awful. And you're right that you would need a more general version of this. You would need something that could account for this right-hand side changing a little bit. But you can do that.
So I guess I can imagine if there's only finite many possibilities for the Tamagawa ratio,
Exactly.
there's finite sum, but in the bad cases, that this is bad.
Yeah, exactly. So you're imagining, in the case that I would put on the board, there's only this finite set V. It doesn't grow with if D changes. And so there's only finitely many possible Tamagawa ratios. So only finitely many possible values of T. You're imagining a case of like an elliptic curve with partial 2 torsion, isogenous to something with a different Galois structure. in that case, yeah, lots of Tamagawa ratios are possible, and so I do sneaky things to avoid thinking about them. Specifically in that particular case, when the Tamagawa ratio blows up, I actually ignore the curve where the Tamagawa ratio blows up and look at the isogenous curve.
But like in the typical case, I don't know, E has no two torsions, then these
Yeah, in this case,
they're
zeta
really
is,
going to be the same thing for
yeah.
whatever x I choose.
it'll be, if m is 1, it'll be 3. It's wonderful.
Okay. So like a side result of yours is just like on any grid, the average is
Yeah,
just 3
you prove, in fact, the distribution of two infinity summer groups is essentially proved on grids and then transported using this proposition.
And you're basically saying it's essentially 3 for whatever nice subset I choose.
The average size of the two summer group is 3 on basically any nice subset of twists for an elliptic curve with full rational, with no rational two.
I'm here a question about, do you have the effective estimate of the H here?
Not in terms of E. No, it's I think it would be useful to have this for like various applications, but it would be large. H needs to be really big because one of these conditions, just to give you a sense of the flavor, is you need to avoid Siegel zeros. And as soon as you're avoiding Siegel zeros, you know, sometimes they're going to be a little bit hairy. Yeah, H needs to be very big, and this was already a complicated enough thing without keeping track of everything. So I was happy to let it slide. But in principle, one should be able to give a bound, but I don't have it. Yes?
So generally, the launch symbol can take a lot of different values, right?
Yes, yeah.
In that case, what's condition 3?
Condition 3. So condition 3, the condition 3 is, I'll answer this question because I can actually write it down, which is sort of unusual. So the relevant field for condition 3 is, you take a look at the splitting field of the two torsion of your elliptic curve. So this is at worst an S3 extension. And then you look at the maximal elementary 2 abelian extension of this that's ramified only at the bad places of E, so at the set B. So this defines some finite field, some finite extension, some finite Galois extension of Q. And then the condition is that the replacement for condition 3 is that for some I less than or equal to k, oh, actually, for each conjugacy class C inside of gal L over Q, there is I less than or equal to k, so fra pi lands inside this conjugacy class, or I guess this conjugacy class. And the assumptions that you make on your grid, I guess I was a little bit sloppy here, but written down properly, this fra pi wouldn't depend on your choice of pi from X. So you would just need a representation of each conjugacy class. And then it sort of proceeds the same as before, that once you have this, you end up with a dual Selmer group whose local conditions are sort of wild at V, but then at all the places I less pi, P1 for pk are that it's trivial, and then this representative things means that you end up with something that's locally trivial.
For the singleton sets,
Yeah.
can you just try to create a small amount of different numbers and then use large sieve on the remaining larger sets?
Yeah, I think that could be a viable alternative. What I have trouble with like one way I like to think about that sort of thing would be basically when you do these problems, you have three types of primes that come up. You have small primes, which are the singleton sets. You have medium primes, and you have large primes. And medium primes and large primes can do the large sig with each other, but medium primes can't do Chebotarev with small primes. What you're suggesting is we also think about the very small primes, and it's hard to draw the line. Yeah, you want to allow for more ramification that goes into V, but then that'll push up what you have to consider for the singleton primes. Like it'll make H have to be bigger, and that's a problem. And so this definition, as I mentioned, as I was writing it down, it sort of drew the lines in arbitrary places, but they are places where I know that the lines work. Possibly the lines would work skipping all the small primes, but I haven't been able to make that work. It would be, yeah, I welcome you to try.
Okay, let's thank Alex one more time. Okay, so the timer is currently 10 past 4. I think we all need a little bit of a breather, so we'll reconvene back here at 20 past 4.